Okay, so welcome to video 4 of our series on hypothesis testing. And we just got done covering section 1.5.14, the very end of chapter 5 in Wessel's notes. And we covered some key concepts that we're going to be making use of in this next section. So this video is on section 2.2 on the null hypothesis and testing of the mean. So let's imagine we have some information from previous studies about some population. Say we know mu and the standard deviation of a known population. And say we take a sample, it could be of that, near that population, or it could be somewhere else. And we're sampling another population that has a mean of mu sub s. So this is the mean of the population in question. And we want to know whether the mean of the population we sampled is the same as the mean of the previously studied or known population. So to answer that question, it's a question. So to answer that question, we're going to formulate some hypotheses. And the first hypothesis we'll formulate is the null hypothesis. And we'll denote the null hypothesis as H sub 0. And in this case, the null hypothesis is that the mean of the population sampled is equal to the mean of the known population. And an important aspect of the null hypothesis is it's formulated as something to reject. And we'll go into more details why later. But for now, what you need to know is the null hypothesis is formulated to be rejected. Okay, and the second hypothesis is the alternative. The alternative hypothesis, and we'll call that H sub 1. And of course, the alternative to this hypothesis is that the mean of the sampled population is not the same as the mean of the previously studied population. So the procedure we're going to follow in answering this question and thus testing these hypotheses is as follows. So our procedure the first part of our procedure is to, of course, sample our population. We have to take our sample and compute the sample mean, because that will be our estimate for the mean of the population. Okay, the second part of our test is to decide on the level of significance. Okay, and that was alpha. And from there, we have to determine z sub alpha, plus and minus z sub alpha divided by 2, that is. And that's appropriate for large samples Or if we have small samples, we would determine t from our t distribution for the appropriate levels of significance and the number of degrees of freedom. Again, for small samples. And we find these by looking them up in a table, or there are actually some tools in MATLAB that you can use. The third step is to convert x bar to z, or t, for a small sample, say n is less than 30. So we'll compute z for large samples or t for small samples. And for an example, and recall that z is equal to x bar, and here we're going to compare it with the population we're testing against, the known population. So this is the mean of the known population. And we have to divide it by our estimate for the standard deviation of our sample mean. And again, that estimate is equal to the standard deviation of the known population divided by the square root of our sample size. So again, mu and sigma are parameters of the population we're testing against. And the final step is to determine if z, or the absolute value of z, is less than or equal to our z at the appropriate level of significance. If that's true, then h naught cannot be rejected. Our sample does not lie out to an unlikely value of z. Alternatively, if the absolute value of z is greater than our critical value, then H1 can be rejected. Okay, so that's our strategy or our procedure. And so let's look at an example. And in this example, say we're given that the mean of our known population is 2.35 grams per cubic centimeter. And so this is following the example given in Wessel's notes, but I'm describing it in a slightly different way, as you can tell. And so this is a density, and it's a density of sandstones. So it's a density of sandstone from a previously studied or well-known outcrop. And we're also given that the standard deviation of density in that outcrop is 0.42 grams per cubic centimeter. So say we sample, it could be a sample from an outcrop that's nearby, or it's just another sample that we take, and we measure a density in our sample of 2.21. And in this example, we're going to say that our sample size is large. Sample size is 50. So we know from our large sample that we have a safe bet that if we were to make repeated samples, our sample means would follow a normal distribution. So we're going to use Z as our key statistic. Okay, so step 2 was to define the level of significance, and to be consistent with Paul's notes, I'm going to define the level of significance to 9.5, and half of that is 4.75. So let's look at our Z table for an alpha over 2, so a probability or a cumulative probability of 4.75, and I see that right down here, and that corresponds to a Z value of minus 1.67. Okay, step 3 was to compute Z of our sample, and that gives, that's 2.21, so minus 2.35 over 0.42 divided by the square root of n, which is 50, gives minus 2.36. And so what we find is that Z is, or the absolute value of Z, is in fact greater than Z at our specified level of significance. So we reject H0 and accept our alternative hypothesis. Now, but if we're wrong, if we're wrong in rejecting H0, then we've made what's called a type 1 error. Okay, there's always a possibility of our sampled population having a mean equal to that of the test population, but we just got a little bit unlucky in that we just happened to sample the population and get an improbable value. So, but what's the probability of making such a type 1 error? Okay, so what's the probability of us making a type 1 error? Okay, why don't you think about that, and if you need to stop the video, go ahead and do that. So that's the question I'm posing. Well, the answer is the probability is equal to alpha, and that's 9.5%. So in other words, of all the possible values of X bar we could have sampled, okay, we've sampled one that has less than a 9.5% chance of sampling it, okay. So if we reject our null hypothesis, then we have this possibility of being wrong.